A force of 6 newtons acts on an object for 10 seconds and the mass of the object is 3 kilograms. What's the object's change in momentum? So we can write the change of momentum like this. That triangle is delta, and that means change, and P is for momentum. One of the equations we can use to calculate the change in momentum is the average force times the change in time. So if you have a force that applies to an object over a certain amount of time, it's going to change the momentum of the object. They gave us the value of that force and the time, so we can just go ahead and plug those in. We got 6 newtons for the force, 10 seconds for the time. So we multiply those together and we get 60 newton seconds for the change in momentum. And that's our answer for part A. Now if we want to know the change in velocity, we have to use the other equation for our change of momentum, which is m delta v. So now we can rearrange this and solve for the change in velocity by dividing by the mass. So now we can take the number that we got before, that's 60 newton seconds, and divide it by the mass of the object, 3 kilograms. And when we do that, we'll get 20 meters per second as our change in velocity. A snow scooter has a mass of 250 kilograms. A constant force acts upon it for 60 seconds. The scooter's initial velocity is 6 meters per second, and its final velocity is 28 meters per second. What change in momentum does it undergo? So we can start with our change in momentum equation as the mass times the change in velocity. Now for the change in velocity, we're going to have to calculate that because we have the final velocity and the initial velocity. So anytime you have a change in something, you can always write that as final minus initial. And now we can plug in the information that they gave us. So we have 250 kilograms. That final velocity was 28, and the initial velocity was 6. So we can go ahead and plug that in the calculator to see what we get. So that's going to give us 5,500 kilogram meters per second. There's a couple different ways to write the units for that, but we'll leave it like that for now. What is the magnitude of the force which acts upon it? So now this is where we got to go back to that other equation. Change in momentum is force times change in time. We know the change in momentum, we just calculated that. We want the force, so we have to divide by the time that they gave us, which was 60 seconds. So we can rearrange that equation for the force and then plug in our numbers. We plug in those numbers, we get 91.6 newtons. A rocket has a mass of 2 times 10 to the 4 kilograms starting from rest and is acted upon by a net force, which was given, for 15 seconds. What is the final velocity of the rocket? So first we can use the force and the time that they gave us to figure out our change in momentum, and then we can use that to figure out the final velocity of the rocket. So change in momentum is force times change in time. Plug in both of those numbers that they gave us. Okay, now this gives us a big number, so I'm going to use my calculator to put this in scientific notation for me. So we'll end up with 2.25 times 10 to the 6 newton seconds. If you notice from the last one, we had kilogram meters per second for change in momentum. Newton seconds and kilogram meters per second, those are both the same units, so they're interchangeable. Now that we have that, we want to figure out what is the final velocity of the rocket. So we can write another equation for our change in momentum as mass times our change in velocity. So we can do v final minus v initial. But they told us it starts from rest. So that means that in this case, our initial velocity is 0, and our change in momentum is just mass times final velocity. Now all we need to do here is rearrange for the final velocity. So you can write final velocity is change in momentum over mass, and then plug in both of our numbers that we've got here. So we use this 2.25 times 10 to the 6 as our change in momentum, and the mass that they gave us, 2.0 times 10 to the 4. So we plug those in and we get our final velocity of 112.5 meters per second. A car with given weight and moving at a certain speed is acted upon by a 640 Newton braking force until it is brought to a stop. We want to know what is the car's mass, what's its initial momentum, what is the change in the car's momentum from that braking force, and how long does the braking force act to bring the car to a halt. So to solve for the car's mass, we've got to go back to our forces section. They give us that weight, which is, another way to write that is the force due to gravity, is m times g. So that number that they gave us, that's the Fg, that's the weight that they gave us. We want to solve for the mass, so we need to divide by g on both sides. Now we can plug in that number that they gave us, 15680 divided by 9.8. That's our constant for g, and then we can plug that in to get our answer for that one, which gives us 1600 kilograms. So that's our mass. Now we want to know what is the initial momentum. So the initial momentum would be whatever speed we're moving at times the mass that we've got. So we can write that as initial momentum is mass times initial velocity. Now we can plug in our numbers to solve for that initial momentum. So the mass that we had was 1600 and that initial velocity was 20. So that gives us 32,000 kilogram meters per second for that initial momentum. Now our next question is, what is the change in car's momentum does the braking force bring about? So we know that this thing comes to a stop, so we can use that to figure out our change in momentum here. So let's get rid of some of this information and then we'll go from there. Okay, so let's use that information to solve for the change in momentum. So we can start with our change in momentum is our final momentum minus our initial momentum. Now in this case it says it comes to a stop, so that means that the final momentum should be 0 because that final velocity is also 0. So our change in momentum in this case is just going to be negative whatever the initial momentum is. So we can plug in the numbers there and we'll get our change in momentum as negative 32,000 kilogram meters per second. Now for the last part, we just need to solve for the force. So we can say that the change in momentum is that force times delta t that we were using before. Sometimes they write average force in there just to say that that force has to be a constant value, but sometimes they don't, so we'll leave that out for now. Now we can solve for the time. In this case, we just need to divide by the force. Okay, so our change in momentum was negative 32,000, and our force, this says that it says a braking force is 640 newtons. Now in this case we're going to have to assume that that is a negative value so that we end up with a positive change in time here. So we can plug those two in and then that'll give us our change in time. Gives us 50 seconds. A car of mass 1,100 kilograms moves at 22 meters per second. What braking force is needed to bring the car to a halt in 20 seconds? So we can start with our change in momentum equation. We can say that's momentum final minus momentum initial. This one is coming to a stop, so that final momentum should be 0. And then we can plug in our equation m times that initial speed in there for the initial momentum. Now we can plug in the numbers that they gave us. And that'll give us our initial momentum of negative 24200. Okay, now we need to solve for the braking force, so we can use the change in momentum is force times change in time, and then we can rearrange that equation to get that force is equal to the change in momentum over the change in time. So we can go ahead and plug our numbers in here. Now if we divide those two, we'll get negative 1210 newtons, and that's our answer. So that force is negative because it's pointing in the opposite direction that our velocity is, which should make sense if we're slowing down. When a bat hits a baseball, the change in momentum of the bat is less than, greater than, or equal to the change in momentum of the ball. So this has to do with collisions, and there's a couple different kinds of collisions which we'll get into, but for now all we need to know is that for collisions the momentum of our system is going to be conserved. So the change in momentum of the bat will be equal to the change in momentum of the ball. When a bat hits a baseball, the change in velocity of the bat is less than, greater than, or equal to the change in velocity of the ball. So now this is where we kind of need to look at our equations for this. So our change in momentum is going to be mass times change in velocity. So we can write this equation for the bat and also for the ball. If we think about the bat compared to the baseball, the bat is going to have a bigger mass. The ball is going to have a small mass. But we said that the change in momentum has to be the same. So to balance this equation, that means that the other term has to go the other way. The change in velocity for the bat should be smaller than the change in velocity for the ball. So if we go back to the question, when the bat hits a baseball, the change in velocity of the bat is less than, greater than, or equal to the change in velocity of the ball. The bat should be this one, less than. We've got a 3.2 kilogram mass moving 4 meters per second west, and then it hits a wall. The wall exerts a force of 250 newtons to the east for 0.07 seconds. Find the final speed and direction of the mass. So let's draw this out a little bit here. So we have a ball heading in this direction, and then it hits the wall, and the wall exerts a force over it over a certain amount of time, and then the ball is going to bounce off the wall and start heading back in the other direction. So we want to find the final speed and direction. So let's set up our change in momentum equation and go from there. So change in momentum, let's start with the impulse side of this equation. So another way to say change in momentum is to call it impulse. And usually when we're thinking about impulse, we're thinking about the forces and the time that the forces apply. So in this case, we have our force times delta t. I'm going to say that going to the right is positive. So in this picture, our force is going to the right. So I'm going to plug in positive 250 newtons, and then that time 0.07. Now if we plug these in, we should get 17.5 kilograms meters per second. So now that we've got our change in momentum, we need to write the other version of this equation, which is going to work with the mass and the velocity. So let's go mass times change in velocity, and then let's rewrite that change in velocity as v final minus v initial. Now we've got to rearrange this equation and solve for that final velocity. So the first thing that we'd want to do is divide both sides by the mass so we can bring that to the other side of the equation. So we'll go change in momentum over mass is equal to velocity final minus velocity initial. Now we want to solve for the final velocity, so that initial velocity has got to go to the other side. So if we add the initial velocity to both sides, that will work for us. So let's go ahead and do that. It's going to be the final velocity is equal to the initial velocity plus change in momentum over mass. So the initial velocity, this is the part we have to be careful because we said that going to the right is positive, but the initial velocity is going to the left. So we've got to plug that in as a negative value when we do this, or we're going to get our signs mixed up. So we'll plug that in as a negative 4 plus 17.5 over 3.2, and that will give us our final velocity. Okay, so we plug that in, we get 1.47, and that's going in the positive direction. So that would be heading east. A rifle accelerates 15-gram bullets from rest to 250 meters per second. The rifle barrel is about 0.8 meters long. We want to find the impulse acting on the bullet and the force on the bullet. So let's start with the impulse. So impulse, we just have to remember that that just means that the change in momentum. So if they say change in momentum or they say impulse, they're talking about the same thing. Change in momentum is going to be mass times change in velocity. Now in this case we're starting from rest, so we know that initial velocity is going to be 0. So we can expand this equation, get rid of the initial velocity term, and we can say that our change in momentum is, in this case, just the mass times that final velocity. Now when we plug this in, we've got 15-gram bullets, so we've got to convert that over to kilograms. So if we divide 15 by 1,000, it'll give us 0.015 kilograms, and then we'll multiply that by the final velocity of 250. Okay, so we'll plug that in. 3.75. Now we want to find the force on the bullet, but we don't know at this point how long it takes to get to the end of the barrel. So we've got to sort out a few things to make that happen. So we can go back to our kinematics section and use some of our equations there to sort this out. So from our kinematics equations, we can say that our change in displacement is going to be 1/2 v initial plus v final times delta t. Then we also know that it starts from rest, so that initial is 0, and then we can use this to solve for delta t. So delta x is equal to 1/2 v final delta t. Now to bring this over to the other side, we can either divide by 1/2 or we can multiply both sides by 2. If we multiply by 2, 2 times 1/2 will cancel out. So we'll get 2 times delta x is equal to v final delta t, and then we can rearrange that to get our delta t. So it'll be 2 times delta x over v final. And now we can just plug in the numbers that they gave us to solve for that. So 0.8 meters long, and that final was 250. So we'll get a really small number here, but that is okay. So it gave this to me in scientific notation at 6.4 times 10 to the negative 3 seconds. Okay, last step is we need to solve for the force, so we can use that using our change in momentum equation and the time that we just solved for. So that force is going to equal change in momentum over change in time. So we got 3.75 and 6.4 times 10 to the negative 3. So this is going to be a very big number. So we get 585.9. Alright, we got a 55-gram pinball moving at 0.6 meters per second, hits a bumper, and then rebounds at 0.75 meters per second. And this takes 1.2 seconds. We want to find the magnitude of the force that acted on the pinball. Okay, so let's draw a little picture again. Let's say we're initially moving this direction, and then it hits a bumper, bounces off, and now it's moving this direction. While it's hitting that, it's going to be a force pointing in that direction. Now we can set up our equation. So our change in momentum is going to be mass times change in velocity. We can rewrite that as v final minus v initial again. Now on the left side, if we want to, we can write this as the force times the change in time. So So we could do this in 2 steps if we want, or we can do this all together in 1 step. Now if we want to find the magnitude of the force, we got to divide both sides by the change in time. So that'll give us mass V final minus V initial over change in time. Now from here we just got to plug in all of our numbers, but we just have to be careful to put our negatives and positives in there properly. So for the mass, we have 55 gram pinball. So if it's grams, we've got to convert it to kilograms, divide it by 1,000. We get 0.055. V final, if we look at our picture, that is going to the left. So V final would be negative 0.75. The minus is built into the equation, and then we have positive 0.6 for the initial because it's going to the right. Now our delta time was 1.2 seconds that took, so we can plug that in, and that will give us an answer for the magnitude of that force. Now in this case we've got 2 negative numbers, so it's going to give us a negative force. So to answer this properly the way that they want, we're going to drop the negative for our final answer. Okay, so we get negative 0.062. So the magnitude of that force is just going to be 0.062. And that's our final answer. Sandbag is mounted on a cart that is at rest on a horizontal frictionless surface, and the total mass is 4.5 kilograms. What will be the velocity of the cart and the sandbag if a bullet of mass 2 grams is fired into the sandbag with horizontal velocity of 550 meters per second? Assume the collision is inelastic. Okay, so we've got to draw a little picture here so we can show what this looks like. So we'll draw an initial picture and a final picture. So initially we've got a bullet which is moving at 550 meters per second, and it is 2 grams for its mass. And then there's a cart that is just sitting here that has no speed, and it is 4.5 kilograms. Then when these two collide inelastically, so what that means is that they're going to stick together when they collide, so the bullet is going to stick in the cart, and then they're both going to be moving together at a new speed that's different than 550. The mass has gone up, so the velocity is going to go down a little bit. So we'll have both the bullet and the cart moving at some unknown final speed, but the mass in this case, the total mass, is going to be the sum of the two masses. So we had 4.5 kilograms for the cart, and then the bullet was 2 grams, so divide by 1,000, be 0.002. So the total mass of these objects is going to be 4.502 kilograms. Now, we know that the momentum is going to be conserved here for all of our collisions, so we can say that the initial momentum is equal to the final momentum, and then we can write an equation for both of these. So for the initial momentum, that's going to be the mass and velocity of both objects, except the cart is at 0. So the cart doesn't have an initial momentum, it's just going to be the initial momentum of the bullet, because that's the only one that's moving. So that initial momentum will be the mass of our bullet and the initial speed of our bullet, and that should be equal to the total mass of both objects and the final velocity of both objects. Now our goal here is to solve for the final velocity, so we can rearrange this equation and plug in our numbers. So we divide by the total mass on both sides, we'll get that we've got the mass of the bullet, 0.002, 550, divided by 4.502. Now plug that in and get this final speed. 1.244 meters per second. Okay, we got two boys with masses that are given. They're sitting on two separate wagons with also have a mass. So it gives us the total mass of the wagon and the person for both cases. They're facing each other and holding a rope between them. The lighter boy pulls on the rope and acquires a velocity of 2 meters per second west. What's the velocity of the other boy? So this is another conservation of momentum question. So for these, I always like to draw a picture for our initial and our final. So initially, we've got two masses. One of them is 60 kilograms, the other one is 75 kilograms, but neither of them are moving. Then in the final situation, the lighter boy pulls on the rope and gets a velocity of 2.0 meters per second west. Okay, so if they're going west, let me write this the other way, so this will make sense with our directions. So let's put the 75 over here and the 60 over here. And now when we draw our final situation, the 60 kilogram person is going to be moving that way at 2 meters per second to the west. And then we want to figure out, okay, how fast would this person have to be moving to make that balance out our momentums. So if we start the same way we did last time, where we said that the initial momentum is equal to the final momentum, the initial momentum, nobody is moving, so nobody has momentum. So that's just 0. So that means that our final momentum, both of the two terms that show up here are going to have to cancel each other out. So if we go mass of person number 1 times final velocity of person number 1, and we add that to mass number 2, final velocity number 2, one of those terms is going to be positive and one of them is going to be negative, and so that will give us an answer of 0 because those will cancel out. So let's say that final velocity 2, let's say that this is the 75 kilogram person, so we'll solve for that one. So we got to subtract m1, the final one, from the other side, and then divide by mass number 2, and that will give us our final velocity. Now we can plug those numbers in. So in this case, mass number 1, that was the one that we knew here, that was the 60 kilograms. And then the final velocity for that person is to the left by 2, so we're going to say negative 2. And then we'll divide by the heavier mass, 75, and that's going to give us our final velocity. So now we can just plug that in to get our final answer. And we get 1.6 meters per second positive, so that means that that is going to the right. Alright, we've got two train cars approach each other with different masses and different speeds. The collision is inelastic, so once they collide, they're going to stick together and move together as a unit. We want to know what is the momentum of both of the cars, and then what's the velocity of the cars after the momentum. Okay, so let's go momentum of heavier car. So let's go momentum initial number 1, let's say, as the heavier car. So the heavier one is going to be 113,000 kilograms times the speed that it's traveling at initially, or the velocity that's traveling at initially, which is 1.2 meters per second. So we can multiply those two numbers together, and we'll get 135,600 kilograms meters per second. Now I've said that this one is positive, so that means that for the lighter car, I'm going to have to say that this one is negative because they're approaching each other. So one of them's traveling to the right and the other one's traveling to the left. So now we can plug in the same numbers that we had here, mass times velocity, but for the other vehicle. Okay, so then we can plug those in. 75,000 times 2.3 is 172,500 kilograms meters per second. And I didn't do what I just said I was going to do, which is make this one negative. So we're assuming that the heavier one is moving to the right, so it's positive. The lighter one is moving to the left, so it should be negative. Now we can deal with the velocity of the cars after the collision. So we can say that our initial momentum is equal to our final momentum. Now our initial momentum is just going to be the sum of the momentum of all the objects that were moving initially. So that'll be momentum number 1, momentum number 2. Now in the final case, it's going to be the sum of those two masses, so whatever the sum of those masses is, times the velocity that they are moving once they stick together. So now we just need to take this equation and solve for that final velocity. So if we do that, we'll get that the final velocity is equal to the sum of those two initial momentums divided by the sum of the masses. Now we can plug those in. 135,600 plus negative 172500 divided by the sum of the masses. 113,000 plus 75000. Okay, now let me plug that in and get our final answer. Okay, negative 0.196 was the correct final answer. Okay, so that's our final velocity. And we got a negative here, so that just means that our final velocity, what ended up happening was we were moving to the left with our final velocity. So when these two trains are colliding, whichever one has a higher momentum is going to dominate in the collision, which was the one that was lighter but was moving at a faster speed. So that momentum was bigger, so that means that we're going to end up traveling in the negative direction when they collide together, and we'll be traveling at negative 0.196 meters per second. We've got a car with a given mass and a given speed, which collides with the rear end of the car in front of it, which also has a given mass and a given speed. If the smaller car is given a speed of 15.3 by the collision, what is the speed of the larger car after the collision? Okay, so this is a bit different than the problems we were just doing, because in this collision, instead of the cars crashing into each other and sticking together as a unit, they're sort of bouncing off each other a little bit. So we can draw our picture again. We've got one car which has a mass of 1,500 kilograms, and it is moving at 15.3 meters per second. And then we've got another car in front of it which has a mass of 1020, and it is moving same direction at 12.5. And then after these two cars collide, sorry, this should be 15.6 to start. Then after they collide, the small car is given a speed of 15.3. So now the big car in the back, we are not sure how fast it's moving. Its final speed is unknown, still 1,500. Then the other car is moving at 15.3. Okay, so now we're just going to have a bunch of different terms when we put this all together. So we can start with our same equation here, that the initial momentum should be equal to the final momentum. Now for each one of these terms, these momentum terms are just going to be mass times velocity. So we can plug these all in from the beginning and then rearrange from there. So in the initial situation, we had one car with 1,500 kilograms traveling at 15.6 to the right, so positive. All of these are to the right, so I'm going to put them all as positive. Then another part of the initial momentum will be the other vehicle, 1020 times 12.5. Then the final momentum is going to be 1,500 times something unknown. That's our final velocity that we're trying to solve for. And then plus 1020 times 15.3. Okay, so now from here we can bring some of these terms over to the other side. So we'll start with dealing with that plus sign that's in the middle. So we'll bring the 1020 times 15.3 over to the other side. So that's going to be, all of this stuff will be the same here. And then we'll have to subtract this term from the other side. Okay, and then once we've done that, then we'll have to divide the whole thing by 1500. And that's going to give us our final velocity. So now I'll go ahead and plug this atrocious looking thing into the calculator and try not to make any mistakes. So that gave me 13.7 roughly, which is what they got, so we are looking good. What will the recoil velocity be if a 3.2 kilogram rifle fires a 0.036 kilogram bullet with a velocity of 290 meters per second? So they're just talking about a fancy term there, the recoil velocity, but it's just the velocity of the rifle after the bullet is fired. So let's draw a picture again. So we've got the rifle, and we've got a bullet to start. We know that our rifle is 3.2 kilograms and our bullet is 0.036. Initially, nothing is moving, so that initial momentum will be 0. Then from there, in the final situation, we will have a bullet which is moving this way at 290 meters per second. So to balance out that momentum equation, that means that our rifle is going to have to be moving the other direction. I'm going to get rid of my arrow here because I don't like it. And this is final velocity, which is unknown, and that's 3.2 kilograms. So we can start the same way we did last time. Initial is equal to final. Now nothing's moving initially, so that's going to be a big fat 0. Then from the final momentum, we've got the bullet, 0.036 times its velocity, 290 positive because it's going to the right. Then we'll have 3.2 times the final velocity, but that's going to the left, so I'm going to stick a negative in here. So we'll say minus 3.2 times V final. Now when we stick this negative in here manually, this just means that we're going to end up with a positive value, and then we have to refer to our picture to figure out which direction it's going. So if we do that, we'll get V final is equal to 0.036 times 290 divided by 3.2. .26 meters per second. And then to answer this properly, to be super specific, I would put in the brackets here to the left. Because we manually put that negative sign in there, it will always make it so that we have a positive value for our answer. So if we want to be super clear, we would say that velocity final is 3.26 meters per second. That's going to the left. Or another way we could write this, if we want it to be a little bit better, is we could say negative 3.26 meters per second. And then it's consistent with the directions that we had from the problem. Okay, a 1,300 kilogram race car is traveling at 80 meters per second, while a 15,000 kilogram truck is traveling at 20 meters per second. Which has the greater momentum? So let's use our momentum equation as mass times velocity. We can plug in both of those numbers for both cases and then see which one is bigger. So we got 1,300 kilograms at 80 meters per second. Okay, we got 10, 40, 0, 0. Then the other one for the truck is 1, 5, 0, 0, 0 times 20. And that gives us 3, 0, 0, 0, 0, 0. Okay, so let's see which one is bigger here. Put some commas in there so it's a little bit easier to read. So it looks like the truck is about 3 times bigger. A 300 kilogram snowmobile is traveling at 30 meters per second. How fast would a 200 kilogram snowmobile need to travel to have the same momentum? So let's start with the heavier one. That one's momentum will be its mass times its velocity. So we got 300 kilograms times 30 meters per second. So that's going to be 9,000 kilogram meters per second for the heavier snowmobile. Now for the lighter snowmobile, its momentum is going to equal its own mass times its velocity. Its velocity is what we're trying to solve for in this case, so we've got to divide both sides by the mass here. We want it to have the same momentum as the other one, so we can plug in that 9,000 kilogram meters per second, and its mass is 200, so then we can divide both sides by 200 to solve for that final, or not final, but just the velocity. Alright, so we plug that in, we get 45 meters per second. A loaded delivery truck has a mass of 5,000 kilograms, is moving at 8 meters per second. The truck is unloaded and travels at 12 meters per second. If the truck has the same momentum in each case, what is the mass of the empty truck? Okay, so similar setup to the one that we had before. We have the loaded truck, its mass times its velocity is going to be 5,000 kilograms times 8. It's going to give us 40,000 kilogram meters per second. Then truck has now moving at 12 meters per second and has the same momentum. So now we've got the same momentum, 40,000 is equal to an unknown mass, but is moving at 12 meters per second. So we've got to divide both sides by 12 to solve for the new mass of the empty truck. Okay, so that gives us 3,333 kilograms. We got a force of 4 newtons is applied to a ball for 0.75 seconds. What is the impulse? So just remembering that the impulse is the same thing as our change in momentum, and our momentum, change in momentum, is force times the time that that force is applied. So we can go ahead and plug in that 4 Newton force, 0.75, and that's going to give us 3 Newton seconds. So the impulse is 3 Newton seconds. A car pulls a trailer with a force of 250 newtons. The total impulse is 900,000 Newton seconds. How long is the force applied? So they told us total impulse was given this time, which is again change in momentum. The force is also given. Now we want to solve for the time in this case. So we just need to take that 900,000 Newton seconds of our impulse and divide that by 250 for the force, and that will give us our value for the change in time. Okay, so that gives us a long time, 3,600 seconds. A model jet rocket applies an impulse of 20 Newton seconds over a 3-second interval of time. What is the force applied? So same setup, just solving for something different this time. We've got our impulse or change in momentum is force times change in time. We want to know the force in this case, so we've got to divide both sides by delta t. Now that momentum, change in momentum was 20, and the time was 3. So that'll give us 6.67 newtons of force. 3 kilogram rock is subjected to the force of gravity for 8 seconds. What is the impulse? So we got to go back to our forces section, and to remind us, we've got an object, the rock, which is 3 kilograms, and it's got its own force of gravity on it. That force of gravity is m times g, where g is the constant 9.8. So that force of gravity that the rock is going to experience is going to be the 3 kilograms times 9.8. Which will give us 29.4 newtons. Now that we've solved for what the value of the force is, now we can go back to our impulse equation and say that impulse is change in momentum, which is force times change in time. Now we know the forces are 29.4 newtons. We know the seconds, 8 seconds, so we can just go ahead and plug both of those in here. So plug that in, we get 235.2 Newton seconds of impulse. A group of people are pushing a stalled car with a mass of 1,100 kilograms. If they push with a net force of 350 newtons for 10 seconds, what is the car's final velocity? Okay, so we can start with our change in momentum equation. Change in momentum, we're going to use both versions of the equation again here. We've got the net force and the time that it takes, so let's say that that's going to be force times delta t. We can go ahead and plug in 350 newtons times 10 seconds. That should give us 3,500 Newton seconds. Now the other version of our change in momentum equation is going to be mass times change in velocity. We can do that same trick that we were doing before, where the change in velocity is final minus initial. And they said stalled car, so I'm assuming that just means that the initial velocity is 0 in this case. So our change in momentum is going to be mass times the final velocity. Final velocity is what we're looking for. We know the mass is 1100, and change in momentum, we had that from the first part. So we can divide both sides by the mass, and that will give us our final velocity. So we'll have change in momentum divided by mass, so that'll be 3500 divided by 1100, and we can plug that in. And we get 3.18. So that's our final velocity. A 40-gram super ball strikes a wall with a velocity of 10 meters per second. Not sure what that is, but that's okay. That is normal to the wall. It bounces away at a velocity of 7 meters per second, still normal to the wall. What is the ball's change in momentum? If the bounce lasted 0.1 seconds, what's the force between the ball and the wall? Okay, there's a lot of words going on here, but really all that we care about is that we've got some kind of initial velocity for this thing, which was 10 meters per second, and 40 grams, so we want to divide that by 1,000 to get that into kilograms, so that'll be 0.04 kilograms is traveling, and then it bounces off a wall. And when it says normal to the wall, all that means is that it's heading towards the wall and it just bounces off, heading back in the same direction. So it's not bouncing like at an angle or anything like that. It's just all in the same line of action. So I'm going to draw it staggered down here, but it's all in the same line of action here. Its velocity when it leaves is 7, and that's going to be in the negative direction, so I'll put a little negative in there, -7. And so we got the same mass, 0.04. And then there must have been some force that made that happen, and that force happened for 0.1 seconds. So now we can put this all together and sort this out. So we're going to go change in momentum. We have more information about the velocities this time, so we're going to start with the velocities and solve for the change in momentum that way. And then once we have that information sorted out, then we'll go to the impulse version of this equation and look at the forces. So we'll go mass times change in velocity, so v final minus v initial. Now we can go ahead and plug in our numbers. We have that mass 0.04. Final we said was -7 because it's going to the left, and then minus initial, so minus +10. Now I'll plug this in to get a number. So we get change in momentum as -0.68. Alright, so we got that. Now we can go over and look at the forces. So now we can say change in momentum is equal to force times change in time. Change in time was given, so we can plug those in and solve for the force. So that change in momentum was -0.68, and the time that we had was 0.1. So we can divide both sides by 0.1, and we'll get the value for that force. Let's get that force as -6.8 newtons, and that'll be our answer. A hockey puck is traveling at 12 meters per second when it is struck by a stick. As a result, the puck travels at 15 meters per second in the opposite direction. If the contact between the stick and the puck lasted 0.05 seconds, what was the force? Okay, so we're going to have a similar setup that we did last time, almost exactly the same except for the last step. So our puck is traveling this way at 12 meters per second, and it's given the mass 0.105. Then it hits a stick. It doesn't say anything about the direction of that the stick's moving, so I'm just going to assume that the stick is like a wall in this case. And then it bounces off the stick, traveling in the opposite direction. So we'll go -15 for that, and still has the same mass. Now the stick would apply a force while it hits it. The force is unknown, and the time that was given was 0.05. Yeah, so it's going to be really similar to what we just did. Okay, so nice and easy then. Do the same thing that we did before. Change in momentum is mass v final minus v initial. Mass was 0.105 kilograms. V final -15. V initial +12. Plug that in and get a number. So we get -2.835 kilograms meters per second. Now we can go to the other version of this equation and solve for that force. So we can plug in our change in momentum that we just solved for. Force is what we want to solve for, and the time was 0.05. So we can divide both sides by 0.05, and that should give us our force. -56.7 newtons. A 400 kilogram jet dragster's engine produces 5,500 newtons of thrust. If the dragster starts from rest, how fast will it be moving after 1.5 seconds and after 3 seconds? So let's set up our equation for change in momentum. We can say that change in momentum is mass times change in velocity again. Now it starts from rest, so that initial velocity is going to be 0. So we'll just have mass times the final velocity. Now we also are going to have two different times here. So to make this a little easier, I'm going to plug in the other version of this change in momentum equation, which is force times change in time is equal to mass times our final velocity. And then I'm going to go ahead and divide both sides by the mass so we can get an equation for the final velocity. So if I bring that over to the side, we'll get force, change in time, divided by the mass. And now we can just go ahead and plug in both versions of the numbers that we were given. So for the first one, we had 5,500. For the newtons, we had 1.5 seconds divided by the mass as 400. So I'll plug in that and we'll see what we get for the first set of numbers. Okay, so 20.6 meters per second. Now, how fast is it moving when after 3 seconds? That's just going to be the same equation, but we're going to replace the delta t with 3 instead of 1.5. And so that should just double the answer that we had here. So if we plug that in to confirm, times 3 gives us 41.2. A loaded barge has a mass which is big and is traveling at 3 meters per second. If a tugboat applies an opposing force of 12,000 newtons for 10 seconds, what is its final velocity? How long will it take to stop the barge? How much force would a tugboat need to apply to stop it in 1 minute? Okay, so we've got the first part, which is the final velocity that we're looking for. So we can say that the change in momentum of our loaded barge is going to be the mass of the barge times final velocity minus the initial velocity. Now the initial, it's traveling at 3 meters per second. The final velocity, that's what we want to solve for. And now we can also do that same trick that we did last time, which is replace that change in momentum with force times change in time. Now we'll get everything all in one equation here that we can work with. So we're going to want to divide by the mass first, so we'll bring that over to the other side. Force times change in time over the mass is equal to V final minus V initial. Now we want to solve for V initial. We want to solve for V final, so we got to add V initial to both sides. So that's going to be force times change in time over the mass plus V initial is equal to V final. Now we've got an equation where we can plug this all in one go. You can also do this in 2 steps. You'll get the same answer here. So you can just kind of do it the way that works best for you. So we got the force, which was 12,000 divided by, times the time, which was 10 seconds, divided by the mass of the barge, 1,500,000, plus the initial, which was 3. Now I'm about to see that this is not going to give us the right answer here, because if we think about what's going to happen is we've got a positive thing and adding another positive thing to it. So we're going to get a speed which is higher than 3 meters per second if we were to plug this in the way that we just set this up. So we have to think about the direction of the force in this equation. It's an opposing force, which means that this has to be a negative value in here because it's supposed to be slowing us down. So now we'll have 3 and then minus some number from that. So we plug this in the way it is now, and it should work for us. As long as I put in the right number of zeros. We get 2.92 meters per second, so that did almost nothing to our speed, just because the momentum of that barge is so massive. So that's our final velocity for the first part. Now for the second part, they want us to figure out how long it will take to stop the barge. So let's erase a few things here. Now we're going to start from here and solve for the time. So if we divide both sides by the force, we'll get mass V final minus V initial over the force. Now we want to stop the barge fully, so that means that our final velocity should be 0 in this case. So we'll get delta t is equal to m times negative vi over that force. We can plug in our numbers here, so 1,500,000 times the initial speed, 3 with the negative in there, and then the force in this case. So the force was the same as before, minus 12,000. Okay, we can plug that in the calculator and get an answer for that. We get 375 seconds. Alright, let's clear off some room and do the last part. Now starting back from here, we want to solve for the force, knowing that it's got to stop in 1 minute. So same as before, we're coming to a stop, so I'm just going to go ahead and get rid of that final velocity term right from the beginning. So we've written this as mass times negative V initial. You can also just bring that negative out to the front side if you want it to be a little bit cleaner, so you can go minus MVI and get rid of those brackets. We're allowed to do that. Then we want to solve for the force, so we got to divide both sides by the time. And plug in again. 1,500,000, initial speed of 3, dividing by the time. It's 1 minute, so we got to convert that over to 60 seconds. And we'll plug this in the calculator. Okay, so we get negative 75000 newtons of force. So that negative just says that it's an opposing force, but the magnitude of that force, you could say, would be positive 75,000 newtons. An Airbus A380 Airliner lands at 30 meters per second, partially loaded. Its mass is 480,000 kilograms. The engine applied reverse thrust for 12 seconds to slow the plane to 25 meters per second. How much thrust do the engines apply? Okay, so there's a lot of fancy terms in here, but basically that thrust is just talking about the force that needs to be applied to slow this thing down. So we can start with where we started with last time, is that our change in momentum is mass times change in velocity. Now we've got the initial velocity, we've got the final velocity given, we've got the mass which was given, and we've got the time. So the next piece for this is just to replace that change in momentum with force times change in time. Now we can go ahead and plug in our numbers if we'd like. So we got the force times 12 seconds, the mass 480,000, and then final minus initial, we were ending at 25 meters per second and we started at 30. So when we plug this in, 25 minus 30 will give us a negative value, which will give us a negative force, which makes sense because this is slowing down. So we can divide both sides by 12, and that should give us our final answer here. other time. Okay, so we get minus 2,0,0,0,0 newtons. So minus 200,000. Okay, stevedore slides a crate along a dock with a 50 kilogram horizontal force of 175 newtons. The opposing force of friction is 120 newtons. If it started from rest, what is the crate's final velocity after 0.5 seconds? Okay, so in this case we've got two different forces going on. One of the forces is going to be used to increase the momentum, and then the friction is going to be sort of taking away from that. So what we've got to do in this case is just figure out what is the net force in this case, and that's what we'll use in our impulse calculation. So we've got 175 newtons of force going that way. The person is pushing the box with 175, but there's friction which is holding us back by 120 newtons. So the net force in this case is going to be that 175 minus the 120. So we should end up with 55 newtons for that. So the 55 newtons, that's the force that we're going to put in our impulse equation when we do our change in momentum. So we say that starting from rest, so we can start with our change in momentum as mass times change in velocity, where the initial in this case, starting from rest, so that should be 0. Then change in momentum, we can replace that with force times change in time. And then we can go ahead and plug in our numbers if we want. We have the force in this case is going to be 55 because it's the difference between those two forces. We've got the time of 0.5. And then the mass of the object is 50, and the final velocity is what we're solving for. So we've just got to take 55 times 0.5, divide that by 50, and we'll get our final velocity. So you get 0.55 meters per second. A rocket sled accelerates to 50 meters per second. When the rocket engine stops, the sled skids along its rails. If the coefficient of friction is 0.5, how fast is the sled moving after 2.5 seconds? Okay, interesting. So first thing I'm thinking about here is that we are not given any mass in this case, so it should cancel out here somewhere. Let's draw a picture and kind of sort it out from there. So initially we're starting at 50 meters per second. And there's some unknown mass. After a certain amount of time, 2.5 seconds, we're traveling at some unknown final velocity, which we want to solve for, and we also have an unknown mass in that case. For the object, if we think about the forces, we're going to have force of gravity going down, normal force going up. This scenario that we're talking about is after the rocket engine stops. So there's no more thrust force that's increasing our speed. The only thing that we have kind of slowing us down here would be our friction force. Now we're not accelerating in the y direction, so the net forces in the y direction should be equal to 0, and the normal force should be equal to the force of gravity, which is m times g. Then we can also use our equation from our forces section, which says that the friction is equal to our coefficient of friction times the normal force. But we know the normal force is m times g, so we can use coefficient times m times g. Okay, now we can go and use this in our other equations. So when we're going and talking about momentum and impulse, the force that we're talking about in this case is the friction force, because that's the direction where our velocity is changing. So in the x direction in this case. So we can go back to our change in momentum equation and say that that is going to be mass times v final minus v initial. So we got the v initial as 50, v final, that's what we want. Mass is unknown, but if we go ahead and plug in our equation for the force, for the impulse, which are force times delta t, and then we go one step further and we replace the force with that equation that we just came up with as mu m g delta t is equal to mass v final minus v initial. Okay, now there's a lot of stuff here, but the reason why we're doing it like this is because we weren't given the mass, so we couldn't just plug in those numbers and then take the result from that and go to the next step. This is a good example of why it's important to practice rearranging your equations first using algebra and then plugging in your numbers as the last step. Because in this case, we sort of have to do it this way. What's going to happen is we have mass on both sides of this equation, so we can divide both sides of the equation by mass and just get rid of it from the equation. Now we've got mu g delta t is equal to v final minus v initial, and then we can rearrange for v final as v initial plus mu g delta t. And now we have all the numbers that we can work with. So that v final, the initial is 50, plus that coefficient of friction was 0.5, g is our constant, 9.8, and delta t was 2.5. So this is definitely a harder question for this section, but a good one to practice. Okay, so the answer we just got was 62.25 meters per second. That is definitely wrong because it's faster than what we started with. So we got to go back and fix it. We've got the friction force here, which we said the magnitude of that friction force was mu mg, but when we plug that into our impulse equation, this is a vector equation, so right here we need to include a negative, which is going to include a negative here, here, and here. And then that will fix our answer. So if we subtract that, we'll get 37.75. Okay, and that looks better because that is slower than what we started with. So I'd like to do that little sanity check and just make sure that the number at least was heading in the right direction. If we were expecting to slow down and we sped up, we know something's wrong. A car slams on its brakes while it's traveling at 8 kilometers per hour. If the coefficient of friction between the tires and the pavement is 0.6, for how much time does the car skid? What if the pavement is wet, reducing the coefficient of friction to 0.3? And then again, what if the coefficient is 0.12? Okay, so let's do something similar to what we just did before. It's going to be the same setup, I believe. So let's go and start with our initial picture. We've got 8 kilometers per hour, so we're going to have to convert that over to meters per second. The mass, again, is unknown. And then it comes to a stop, so we end up with 0 final velocity and unknown mass again. Now, this is going to be the same setup that we had before, where if we do a free body diagram, we're going to have force of gravity going down, normal force going up, friction force, which is slowing us down, and if we go through the same process that we did in the last question, we'll end up with the friction force is equal to mu mg. And that just comes from setting the net forces in the y direction equal to 0 and going from there. So our change in momentum is going to be equal to mass v final minus v initial. Now the one place you do want to plug in numbers right away is if you know something is 0, then just go ahead and plug that in as 0. It'll make this way easier to rearrange. We know that final velocity is 0, so we can plug that in. And then we have 0 minus v initial. We can write that as negative mvi when we simplify that. Now that change in momentum, again, is going to be force times delta t. And then we'll remember to put our negative in there this time. That force is going to the left, so that should be negative mu mg delta t is equal to negative mvi. Now we're solving for the time in this case, so we can go and clean this up. Our negatives are going to cancel on both sides. Mass is going to cancel on both sides, and we can divide by mu and g, so we'll get that delta t is equal to the initial speed divided by mu g. And now we can just go ahead and plug in those three different numbers to see what we get. So we've got the initial speed in there, which is 8 kilometers per hour. We can convert that over. So I'll write it like this, we're 8 kilometers per hour. We'll set up a little fraction to convert the kilometers. We want to get rid of kilometers and replace it with meters so that our kilometers will cancel. 1 kilometer is 1,000 meters. Okay, so let's convert this one over to seconds. So we'll put hours on the top, seconds on the bottom. 1 hour is 60 minutes, which is 60 seconds. So that's 3,600. So we'll go 8 times 1,000 divided by 3,600 is 2.22 meters per second. So we'll have 2.22 meters per second. We're going to plug in a few different values for mu, and then we'll have g as 9.8. Okay, so let's plug in all three of these and see what we get. So for the first one, this is going to be 0.6 that we're plugging in for mu. So it'll be 2.22 divided by 0.6 and 9.8. And that gives me 0.378 seconds for the first one. Now we're just going to go and change that number. So if we change it to 0.3 for mu, we'll get 0.755. And then we'll change it again to 0.12, which gives us 1.89 seconds. A force of 767 newtons is needed to push a car across a lot. 2 students push the car 28 meters. How much work is done ignoring friction? And suppose they complete this task in 58 seconds. How much power will they generate? Okay, so first up, work is equal to force times distance. So the force that they applied was 767 newtons, and the distance was 28 meters. So we can just go ahead and plug those in, multiply those two numbers together, and that will give us 21476. Now the units for this was we had newtons times meters. That's newtons times meters is the same thing as a joule. So our work will be 21476 joules. Now we want to know if they complete this task in 58 seconds, how much power will they generate? Now power is just work over time. So the work was 21476 joules, and that took them 58 seconds. So we can go ahead and divide those two numbers. And then we had joules divided by seconds, so that's our definition of watts. So that's going to give us 370 watts. How much work is done by a forklift raising a 688 kilogram piano by 2.8 meters? So we said from before that our work is equal to force times distance, but we don't have a force yet, so what we need to do is find the force from gravity from that piano, because that's the force that you would need to apply to lift it up. So the force due to gravity is mg, m times g. So we can go ahead and plug that into our equation. So that's going to be mg times distance. And now we can fire all the numbers into that. So we had 688 kilograms, 9.8 for value for G, and then we're raising this by 2.8 meters. 688 times 9.8 times 2.8 gives us 18878. And let's round that to 79 joules. Okay, now same as before, we want the power here, so we can take that work that we had, certain number of joules, and divide it by the time that it takes to do it. $258.6 watts. Okay, a couple questions about work and power. So the first one, is work a vector or a scalar? So we have to remind ourselves, what does it mean by a vector or a scalar? I'll give you some examples first of each one, and then we'll decide what is common about those. So for a scalar, an example for that would be time or mass. An example of a vector would be velocity, acceleration, or displacement. Okay, now the difference between those two is the scalars, they only have a magnitude. The vectors have a magnitude and a direction. So if a certain quantity only has a magnitude, it would be a scalar, and if it has a magnitude and a direction, then it's going to be a vector. So when you say something like the velocity is 50 kilometers an hour, you're not quite stating that properly, because you need to tell me which direction we're moving in. So when we're talking about velocity specifically, we would need to know the speed that you're moving and the direction that you're moving. For something like mass, if it's 12 kilograms, there's no direction associated with that, so that's a scalar. Now, is work a scalar or a vector? Work is a scalar. It has no direction associated with it. Work is measured in what units? Well, we can always work this out if we need to, if we forget, but work is force times distance. Force is in newtons, distance is in meters, so our work is going to be Newton meters. Another way to write that is joules. Power is measured in what units? Same as before, power is work over time, and work is measured in joules, time is measured in seconds. So we get joules over seconds, which is watts. What is the minimum power generated by a 64 kilogram person who climbs 82 stairs? Each stair has a height of 21 centimeters in 83 seconds. Okay, so each stair is 21 centimeters and we go up 82 stairs. So we got to find the total distance or the total height that we're climbing here. So we got 82 stairs and 21 centimeters. So let's go and multiply those two together just to figure out how high we're actually climbing. That gives us 1722 centimeters. Now we're going to want this in meters for our calculations to work out properly. So we can get rid of the centimeters, convert to meters. 1 meter is 100 centimeters. So if we take that number and divide it by 100, that'll give us 17.22 meters. Okay, so that's the height that we climb. Now, same as before, we need to figure out a force based off a mass. So the force in this case is going to be our force of gravity, which is m times g. So the mass is 64 and g is 9.8. So we can take 64, multiply it by 9.8. It's going to give us 627.2 newtons. Now we can go to our power calculation. So we said that power was work over time, but we also know that work is force times distance. So we can plug that into our equation and then plug our numbers in. We've got the force, 627.2, the distance of 17.22 meters, and we're dividing that by the time, which was 83 seconds that it took to do that. So now we can take all these numbers, put them in the calculator, and get our answer for this one. So we end up with 130. Alright, an electric motor lifts a 25 kilogram load of vertical distance of 24 meters in 32 seconds. What's the power output of the motor? And then our next part is going to talk about efficiency. Okay, so power output of the motor. Okay, so this is going to be similar to what we just did before. So we're going to say that power is equal to work over time. The work is force times distance over time. The force in this case is the force due to gravity to lift this thing up, and the force due to gravity is mg. So we'll get m times g times distance, all divided by time. So we got the mass of 25 kilograms, g is our constant, 9.8, distance is 24 meters, and the time was 32 seconds. That gives us 183.8, let's say, watts for the motor. Now for the second part, we want to know the efficiency. So we can use one of our equations for efficiency. I always like to draw a little picture when we do this as well. So this is, sometimes I call this like a energy diagram. So we said that the power out that we're getting, that's what we just calculated. That's that 183.8. That's the useful amount of power that we got out of this motor. Then some of the power is going to be lost. We're not sure how much of that is. And then to make up for both of those, we've got to supply a certain amount of power to the motor. We want to figure out the efficiency, and we know that the power going in is 244 watts. So we can calculate our efficiency by taking the power output and dividing that by the power input. One way that's helpful to remember this is that this should always be a decimal number when we calculate this. So if you do this the wrong way around, you'll get a number that's bigger than 1. So we got a decimal number of 0.75, which means we are on the right track. So to put this into a percentage, if you want, you can multiply it by 100, and that would give you 75%. So we apply 244 watts of power to the motor. It's 75% efficient, so 75% of that energy is used for useful work, and the other 25%, that would be lost to things like heat. 65 Newton force is horizontally applied to a mass of 12 kilograms sitting on a level 4 floor for a distance of 14 meters. How much work did the applied force do? And then the next parts, we got friction, and then we're looking for the net work on the mass. Okay, so let's start with the work of the applied force. So we've got work is equal to force times distance. Now we've got 65 newtons of force, and we got 14 meters. So we can take 65 and multiply it by 14, and that gives us 910 joules. Now there's a coefficient of friction of 0.25, so we've got to figure out how much work does friction do. So if we draw our little picture again, we've got our force of gravity going down, normal force going up, there's this applied force, and then there's also a friction force. So we derived this out earlier in one of our other questions, but from the net force in the y direction equal to 0, that will give us that our normal force is equal to m times g, and then our friction force, the equation for that is the coefficient of friction times the normal force, so that'll be coefficient of friction times m times g for that friction force. They give us the mass in the problem, so that's good, we can work that out. Let's go ahead and plug those numbers in. That was given to us as 0.25 for the coefficient, mass was 12, and g was 9.8. So I'll plug that into the calculator. 0.25 times 12 times 9.8 gives us a friction force of 29.4 newtons. Now when we go and do the work from the friction force is pointing in the opposite direction that we're traveling in. So that means that the friction force is going to give us a negative work because it's taking energy out of the system. So we've got to put a negative friction force times distance. So that's going to be negative 29.4 times 14 meters. So that gives us negative 412 joules. Now, when they're talking about the net force, anytime you hear the word net, that just means that you got to add up everything. So that's going to be the work done by the applied force, positive, plus the work done by friction, which is a negative value. So we're going to end up subtracting those two numbers. So it's just going to be 910 minus 412. So you can think of it as like we added 910 joules from that applied force, but the friction force took 412 joules away. A 12 Newton object is lifted at a constant velocity from the floor to a height of 2.3 meters. How much work is done on the object against gravity? Now in this case, they told us the object was 12 newtons, so instead of giving us the kilograms, they actually gave us the force of gravity as 12 newtons. So that's weight was given to us. So that means that we can just go ahead and plug that into our equation. Work is equal to force times distance. The force was given as 12 newtons, so no need to multiply that by g again. And it lifted a height of 2.3 meters. So we can just take 12 and multiply it by 2.3. We get 27.6 joules. How much work is done on an 11 kilogram object to accelerate it from 15 meters per second to 20 meters per second in 4.3 seconds? Okay, so they gave us a few different pieces of information here, which we might not need all of them, but that's okay. The other way that we can think of work is how it relates to energy. So our work is going to be equal to the change in energy of our system. In this case, the energy that we're changing is going to be the change in kinetic energy. So we can write that as kinetic energy final minus kinetic energy initial. The equation for kinetic energy is going to be 1/2 times the mass times the velocity squared. So that's going to be 1/2 mv squared final and 1/2 mv squared for the initial. Now we know the initial and final speeds, we know the mass that was given, so we could just go ahead and plug those numbers in. 1/2 times the mass of 11, final velocity was 20, mass and initial velocity of 15. As long as we're in our base units here, everything is going to work out in terms of units, so we should just end up with joules here again. So we get 962.5 joules. A 7.6 kilogram object is pulled 6 meters at a constant velocity of 5 meters per second along a horizontal force of 2 newtons. What is the work done on the object to overcome friction? So what we can assume in this case, because we're being pulled at a constant velocity, is that the force that we're applying should be the same as whatever the friction force is. So the work done to overcome friction, we can work that out here by drawing a little picture again, free body diagram. Force of gravity is going down. We get some applied force moving us forward. Normal force going up. Friction force going back to the left. Okay, now that we've got our picture, we can do the forces in the x direction, our net forces, should be equal to 0 because we're moving at a constant velocity. So that applied force should balance out perfectly with our friction force. And so that means that our friction force should be equal to the applied force. And the applied force, they said that was 2 newtons. So now we got a value for our friction force. We can go ahead and plug that into our equation for work, just putting a negative next to that because we know that that's friction force is pointing in the opposite direction that we're moving in. So we got to put a negative in there. We got 2 newtons for the force, and the distance is 6 meters, so we should end up with negative 12 joules. So the work done by friction would be negative 12. So that means that the work done to overcome friction, the work done by the applied force, should be positive 12 joules, because those should cancel each other out. What is the gravitational potential energy with respect to the ground of a 20 Newton object that is 2 meters above the ground? Okay, so let's draw a little picture. We've got an object up here, and our ground is down here. So that's our 2 meters from here to here. And our ground is our reference, so this is where we're taking our measurements from for the height of the ball. Now our equation for gravitational potential energy, sometimes I write this as PEG or just EG, is mgh. In this case, we don't know the mass, but we know the force of gravity is 20 newtons, and the force of gravity is mg. So we can actually replace that in this equation and just go force of gravity times height. Then we've got 20 newtons of weight, and it's 2 meters above the ground. So we're going to end up with positive 40 joules as our answer. Calculate the kinetic energy of a 1,250 kilogram car traveling at a speed of 40 kilometers per hour. So let's take that speed and convert that over to meters per second first before we do anything. We've got 40 kilometers per hour. I'm going to go set up my fraction here. I'm going to get rid of the kilometers and replace it with meters. So those will cancel out. 1 kilometer is 1,000 meters. And then we got hours on the bottom, so we got to put hours on the top to cancel those out. And we want seconds. 1 hour is 3,600 seconds. So we take that speed, multiply it by 1,000, divide it by 3,600, and we'll get 11.11 meters per second. Now our equation for kinetic energy is going to be 1/2 mv squared. So we can just go ahead and plug in the numbers that we got there. 1/2 times the mass, 1250, times the velocity squared. Put that in the calculator. That gives us a big number, 77,160 joules. What speed would a heavy object hit the floor if it was lifted vertically from the ground at a constant speed of 1.2 meters per second for 2.5 seconds and then dropped? Okay, so lifted from the ground at a constant speed, and then what speed would it hit the floor? Okay, I see. So we got to break this into two parts. So part number one is we're going from the floor up to some height. So draw our floor over here. We're starting down here. We're moving at 1.2 meters per second for 2.5 seconds. And then that's going to get us up here somewhere. And then from there, we're going to be dropped until it goes back down here, and we're going to find some final speed before it hits the ground. So let's deal with the first part here. So for part number one, this is just a straight up kinematics problem. So we can say that our velocity is displacement over time. Because we're moving at a constant speed, we're allowed to use that equation. Then we want to solve for the distance in this case, so we got to multiply both sides by time. So we'll get Vt is equal to the distance. That velocity that we had was 1.2 meters per second, and the time was 2.5 seconds. So we can multiply those together, and that'll give us 3 meters. Okay, so now for part two, we're starting at a certain height and then we're dropping this ball. So we can use the conservation of energy for this. So what we can say is whatever energy we have in our initial state should be equal to the energy we have in our final state. Initially, we have potential energy, so that's going to be mgh. And in the final situation, we've got rid of all of our potential energy and we've converted it to kinetic energy, so that's going to be 1/2 mv final squared. Now this is going to be another one of those ones where the mass just cancels out from both sides, so we can get rid of that from our equation. It's always a good hint if the question doesn't give you mass and it seems like you're going to need it, is that there's probably a way that you can set up your equation where it'll cancel itself out. Now we need to solve for this final speed, so let's multiply both sides by 2. So we'll get 2g times that initial height is equal to v final squared. And then to get rid of that squared, we've got to square root both sides. So it would be the square root of 2g times that height is equal to v final. So now we can go ahead and plug in our numbers and then square root this thing. So 2 times 9.8 times that height that we had from the beginning, which was 3. We'll plug that in. That gives us our final speed of 7.67 meters per second. We got a 3 kilogram object which travels vertically at a constant speed. What is the increase in gravitational potential energy after 5 seconds? Okay, so similar setup to before. Let's find the height that we're traveling here. So we're going up at a constant speed of 1.5 meters per second, and we do that for 5 seconds. So we'll start with velocity is distance over time, which we can use for constant velocity problems. And then we can rearrange that the same way we did last time, which is going to be the distance is equal to velocity times time. We've got 1.5 meters per second. And we're traveling for 5 seconds. So that should give us 7.5 meters. So that's how high we travel. Then the increase in gravitational potential energy. So our change in potential energy is going to equal mass times g times our change in height. So we got the mass this time was given as 3, g is 9.8, and our change in height was 7.5 that we got from the first part. So that gives us 220.5 joules. A heavy object was dropped from some distance above the ground. When it reached the ground, it had a speed of 11 meters per second. From what height was the object dropped? So we can do a little initial and final to figure out what's going on here. So initially, we have no speed, and we're a certain height from the ground. Then after some time, just before we hit the ground, we've got no more height anymore, but we have some final speed that we'd be looking for. So same as before, we can say from the conservation of energy that the energy that we have in the initial is equal to the energy in the final. Initially, we have no speed, so we have no kinetic energy, but we do have potential energy. In the final, we're just about to hit the ground, so we've got no more potential energy, but we do have kinetic energy. So this will work out the same way it did in the other problem. And then we can solve this the same way. So cancel out those masses, get rid of those. So we're actually looking for the height in this case, so let's go and rearrange this. Let's divide both sides by g. So we'll get 1/2 v final squared over g. Okay, so the height initial, 1/2 times v final squared, so that v final should be 11. So we'll go 1/2 11 squared divided by 9.8. That gives us 6.17 meters. Alright, a roller coaster problem. A roller coaster is traveling without friction as shown in the diagram. If the speed of the roller coaster at A is 3.0 meters per second, then what is the speed at E? Okay, so there's a lot going on here. They got a bunch of different states that they've drawn in this picture. But the thing to keep in mind is that it does not matter what is going on over here. Because the energy is conserved in this case, the energy is going to be transferring between potential energy to kinetic energy back and forth a couple times. But all that we really care about is what's going on at A and what is going on at E. So we can start by saying that our energy initial is equal to energy final. Initially, we have a height of 8 meters and we have an initial speed. So we're going to have 1/2 mv initial squared plus mg height initial. So we've got some kinetic energy and we've got some potential energy in the initial state. Then over at the final state, if we make our reference for our height kind of that level right where E is, then we're not going to have any more potential energy. But we will have some more kinetic energy. So we'll have 1/2 mv final squared. Okay, so same as last time, divide both sides of the equation by mass and get rid of it. Gone from the equation. Then this will make this a little bit easier to solve. We can also multiply everything by 2. So we've got this v final that we're trying to solve for. If we multiply everything by 2, 2 times 1/2 is going to disappear, so it'll cancel itself out, so it'll just be vi squared. Then we'll have to multiply each term by 2, so it'll be 2ghi, and then 2 times 1/2 will cancel out, so it'll be v final squared. Now we can go and solve for v final and square root this thing. So when we go and solve for this, it's going to be the square root of all of this stuff. Okay, then we can go and plug in our numbers, do that up here, get a little bit more room. So v initial, so that's going to be 3 squared plus 2 times 9.8 times that initial height of 8. Okay, now we'll plug this in the calculator to see what we get, which gives us about 12.9 meters per second. force is required to accelerate a 50 kilogram object from rest to 5 meters per second along a 3 meter horizontal frictionless surface? Okay, so we're talking about work in this case. We're talking about forces in this case, so that's going to be related to work. And then we also have some energy terms showing up here as well. So let's go with this equation. Work is equal to change in energy. Then we know from previous questions that the equation we can use for work is force times distance. And in this case, our change in energy is going to be our kinetic energy, change in kinetic energy. So that'll be final minus initial for kinetic energy. We're starting from rest, so that kinetic energy initial is going to be 0. We've got 0 velocity initially, so that will be gone. Then we can write this as force times distance is 1/2 mv final squared. Now we're trying to solve for the force in this case, so let's rearrange for F. We'll divide both sides by the distance, and we can plug our numbers in here. 50 kilograms, 5 meters per second, and a distance of 3 meters. To 208.3 newtons. What is the average power of a 50 kilogram sprinter accelerating from rest to 1.5 meters per second in 4 seconds? Okay, this is another equation for power that we've sort of looked at so far in this video, but not quite. So from before, we said that power is equal to work over time. So from this question, they gave us the time in this case, but we need to figure out the work. So we can also say that the work is equal to the change in energy. And now we've got to figure out the change in energy going from 1.5 meters per second from rest to 1.5 meters per second. So our change in energy is just going to be the change in kinetic energy. So that's going to be kinetic energy final minus initial. Starting from rest, so that's going to be 0. Final is 1/2 mv final squared. So let's go ahead and plug those numbers in. 1/2 times 50 times 1.5 squared. So we get 56.25 joules, and then we can go and plug that up here. So 56.25 divided by the time, which was 4 seconds. That gives us about 14 watts. An electric motor is used to lift an elevator and occupants with a given mass to a height of 15 meters in 30 seconds at constant velocity. What is the power output of the motor? Okay, let's see. So, start with that equation that we had from last time. Power is equal to work over time. The work in this case, we could think of this as change in energy again. In this case, we're moving at a constant velocity. So the change in energy that we're working with is not to do with the change in kinetic energy, it's the change in potential energy. Because there is no change in velocity, so that means no change in kinetic energy. So our change in potential energy in this case is going to be mg delta h. And we've got that mass given 1.5 times 10 to the 3. 9.8, and our height, we went up by 15. So let's work that out. As 220,500 joules. Now we can take that number and put that up in this equation. So we get that amount of joules, and that was in 30 seconds. So we take our answer and divide that by 30, and we get 7,350 watts. Okay, 1 times 10 to the 3 kilogram object is raised vertically, constant velocity by a crane. What is the power output of the crane? Okay, now it seems like they're giving us less information here, so let's work this out here. This is kind of a unique equation for power, but it shows up every once in a while. So we can think of what power as, start with this equation. Power is equal to work over time. But we also know that work is equal to force times distance. So there would have to be some force that's applied to this crane to raise it up. But we can also use the fact that velocity is equal to distance over time. So see this part in here, we have distance over time. So we can actually swap that out and say that power is equal to force times velocity. So as long as we're moving at a constant velocity, with a constant force, we can use this equation. So that means we can just plug in the numbers that they gave us here, except for this force is actually going to be the force due to gravity, so that's going to be mg. So one extra step. Now plug in. 1 times 10 to the 3, 9.8. Velocity was 4. And that gives us 39200 watts. How much work will you do if you push a block of concrete 4.3 meters along a floor with a steady force of 25 newtons? Okay, nice and easy one for us. Work is equal to force times distance. They gave us both those numbers, so we can fire those in there. 25 newtons, 4.3. Calculator time. 25 times 4.3 is 107.5 joules. If your mass is 70 kilograms, how much work will you do climbing a flight of stairs 25 meters high, moving at a steady pace? Okay, so work is equal to force times distance. In this case, the force that we're talking about would be the force to overcome the force of gravity. So we could do mg as the force times distance. And we got 70 kilograms, 9.8 for g, and a distance would be the height that we're traveling as 25 meters. And that gives us 17150 joules. Your car is stuck in the mud. You push on it with a force of 300 newtons for 10 seconds, but it will not budge. How much work have you done in 10 seconds? Okay, so this question is setting us up to trap us a little bit. Work is equal to force times distance. We are stuck in the mud, so it does not budge, it does not move. Distance is equal to 0. So we have that force of 300 newtons multiplied by a distance of 0, which just gives us 0. We did no work because it did not move. A girl uses a 3-meter long ramp to push her 110 kilogram motorbike up to a trailer which is 1.2 meters above the ground. How much work is done on the motorbike? Okay, so we got our ramp. Let's draw this out here. So the ramp is 3 meters long, so that's like the hypotenuse of that triangle. But it's only 1.2 meters above the ground vertically. So even though you're moving 3 meters along the ramp, the height that we're changing is 1.2. So you could think of it as like, this is probably an easier way to set up this equation, is if we go work is equal to change in energy, And the change in energy in this case would be our change in potential. So this would be change in potential energy, which is going to be mg delta h. So delta h is always measured vertically in this case, so we don't actually care that it went 3 meters along the ramp. All that we care is that we went up by 1.2. So we got 110 kilograms, 9.8, and we went up by 1.2. One, 2, 9, 3.6 joules. Okay, probably could have rounded that better, but we'll leave it like that. A force was used to push a box along the floor a distance of 8 meters. If 160 joules of work was done, what force was applied? So, work is equal to force times distance. They told us that the work in this case was 160. The force is unknown, but we know that it went 8 meters, so we can take 160, divide it by 8, and that should give us our force, and that will give us 20 newtons as our force. A force of 50 newtons is used to do 480 joules of work. What is the distance that the object was moved? So same equation, solving for something different this time. Work is equal to force times distance. We got 480 joules. Our force was 50, and our distance is unknown. So we can divide both sides by 50 and solve for that distance. And that gives us 9.6 meters. A bulldozer pushed a large rock with a force of 5,000 newtons at a constant speed of 2 meters per second for 20 seconds. How much work was done? Let's go with velocity is distance over time. Let's just go ahead and rearrange that for the distance. And then we can just go ahead and plug those in. So velocity was 2 meters per second, and we had 20 seconds. Okay, so that should give us 40 meters. And then we can go find our work from this. Force times distance. Our force was 5,000. And our distance was 40. Okay, so we put that in scientific notation. That'll be 2 times 10 to the 5 joules. A 50 kilogram box is pulled 11 meters along a level surface by a rope. If the rope makes an angle of 35 degrees with the ground and the force exerted through the rope is 90 newtons, how much work is done on the box? Okay, so let's draw a little picture. We've got this box on the ground. It's being pulled by a force, and it makes an angle of 35 degrees. So we've got this force like this from this rope, 90 newtons, and then this angle in here is 35 degrees. The direction that we're moving is this way in our picture. So to use that equation that we were using before, where we said work is equal to force times distance, it's got to be the force that points either in the same direction as the distance or exactly the opposite direction. So because our force is off at this weird angle, we've got to use a little bit of trigonometry to work that out. Let's draw a triangle. We've got 90 newtons over here. The force that we want to use in this equation is this one, and then we've got the angle of 35 degrees. So we can work this out with trigonometry by saying that cos theta, so cos 35, is equal to the adjacent, which is f, the side which is right next to the angle, divided by the hypotenuse of 90. So if we multiply both sides by 90, we'll have 90 cos 35 is equal to that force. So we can plug that into our calculator, making sure our calculator's in degrees mode and not radians. It will give us 73.7 newtons for that force. Now we can plug that into this equation. So work is equal to 73.7 times the distance of 11. And that gives us about 811 joules. How much power does a crane develop doing 60,000 joules of work in 5 minutes? Okay, so we got power is equal to work over time. We've got our work of 60,000 joules, and then our time here, we got 5 minutes, so we've got to convert that minutes times 60 seconds per minute. So if we take 60,000 divided by 5 and 60, that'll give us 200 watts. How long does it take a 2.5 kilowatt electric motor to do 75,000 joules of work? Okay, so that telling us that it's 2.5 kilowatt motor, that's telling us that the power is equal to 2.5 kilowatts. Now if we want to convert that over to watts, we need to multiply that by 1,000. So that'll be 2,500. And then we're trying to solve for time here, so let's go to our equation. Power is equal to work over time. So we've got the power as 2,500, the work as 75,000, and then the time is what we're trying to solve for. So we can multiply both sides by time, bring that up over here. And then divide both sides by 2,500. Okay, now we plug that in. That gives us 30 seconds. How much work can a 500 watt electric mixer do in 2.5 minutes? Okay, so let's start with our power is equal to work over time. Then they've given us the time, they've given us the power, we got to solve for work. So if we multiply both sides by time, we get time times power is equal to work. And then we can plug in our numbers here. So I'm just going to put this in the other order. Work is equal to time, 2.5 minutes. Let's convert that over to seconds at the same time. So minutes on the bottom, seconds up top. 1 minute is 60 seconds. We'll be left with seconds for our units. So that whole thing is the time in seconds. Then we got to multiply that by the power of 500. Okay, so to plug this in, we're just going to go 2.5 times 60 times 500. And that gives us 75,000. A crane lifts a 1,500 kilogram car 20 meters straight up. How much potential energy does the car gain? So our change in potential energy is going to be mg delta h, the equation for that one. Then we've got that mass there as 1,500. G is 9.8. And our change in height, we went up by 20, so that's going to be positive 20. Now we work that out. 1,500 times 9.8 times 20 is 294,000. So that's how many joules that we got. That's the change in potential energy. Now the work, how much work must the crane do? The work is equal to the change in energy. And in this case, the only energy that we're changing is that potential energy. So it's just going to be equal to that exact same number, 294,000 joules. Alright, we got a 4 kilogram rubber ball drops from a height of 5 meters to the ground and bounces back to a height of 3 meters. How much potential energy does the ball lose on the trip down to the ground? Let's start with that. So we've got a ball which is going down by 5 meters. So our change in potential energy for that first part is going to be mg delta h. The mass of 4 kilograms, g, and delta h, we're going down by 5 meters, so we're going to put in a -5 in this equation this time. So we have lost 196 joules of energy on the trip down to the ground. Then for part B, how much potential energy does the ball regain on the trip back up? So we can use the exact same equation. Change in potential energy is mg delta h. So we're still going to have 4 for the mass, 9.8 for g. And our change in height this time is we're going up by 3. So it's going to be +3. So that gives us 117.6 joules. What is the net loss of potential energy during the bounce? So the net loss of potential energy is just going to be the difference between those two numbers. So we started with 196 joules at the beginning, and at the end we ended up with 117.6. So it's just going to be the difference between those two. So the potential energy that we lost is going to be 196 minus 117.6, which means that we lost 78.4. What is the kinetic energy of a 0.5 kilogram ball thrown at 30 meters per second? Okay, easy one to finish off this section. Kinetic energy is 1/2 mv squared. And then we just plug our numbers in. We got 0.5 for the mass. We got 30 for the velocity. So now we can plug that in. And don't forget to square it as 225 joules. Okay, the last few questions that we have are on efficiency, so let's start this off with our efficiency equation. This is what we get out divided by what we put in. So our energy out in this case was 30 joules, and we put in 95 joules. So we can divide those two to get our efficiency. Now when we do this, it's going to give us our efficiency as a decimal, so it's going to be 0.316 as a decimal. If you want to represent that as a percentage, you just need to multiply it by 100. So if we multiply that by 100, it's going to be 31.6%. Calculate the percent efficiency of a motor that produces 450 joules of mechanical energy while using 6,500 joules of electrical energy. Okay, so they're telling us like that it's different types of energy. That's not super important here. It's going to be using that same equation that we did before. We got out 4,500 joules and we put in 6,500 joules. So let's go ahead and just multiply that by 100 while we're doing that to get that into a percent. Usually just do that at the same time. So 4500 divided by 6500 times 100. And that gives us 69%. A car produces 27.5 kilojoules of useful output energy from 125 kilojoules of fuel. What's the car's percent efficiency? So same deal as before. It's what we get out over what we put in. We get out 27.5. Now in this one we have kilojoules. Let's write the units in here. So we have the option to convert this over to joules, but it's going to be a little bit faster if we just don't do that because they're both in kilojoules. As long as we're in the same units, both of those units will cancel out. So kilojoules over kilojoules is just no units, so that works out okay. Now let's plug this in. 27.5 over 125 times 100 is 22%. A dry cell has an input energy of 85 kilojoules and an output energy of 7 kilojoules. What is its efficiency? Okay. So 7 over 85, using the same trick as before with the units. 100%. And we get 8.24, let's say. Now we know this percentage is going to be somewhere between 0 and 100. So the most common mistake is that people get the fraction upside down on this. So instead of 7 over 85, they'd go 85 over 7. You know, if you get a percent that's like 400% or something, then you probably just got the fraction upside down. Okay, this one's a little more exciting. A kettle has a power rating of 1,000 watts. It takes the kettle 4 minutes to heat 600 milliliters of water from 22 degrees Celsius to 100 degrees Celsius if it uses only 54.4 watt hours of energy to heat the water. What is the efficiency of the kettle? Okay, so this is significantly harder than the last couple questions that we just did, but let's break this down piece by piece. So the kettle has a power rating of 1,000 watts. It takes the kettle 4 minutes to do its thing. So let's start with that. So we've got the power. Let's say the power in this case, is that 1,000 watts that we're working with. Then it takes 4 minutes to heat up some water. So let's go ahead and convert that and figure out how many joules this would be. So this would be like the amount of energy that we put into the kettle is going to be our power times our time. So that's going to be our 1,000 watts times that 4 minutes, but we want that in seconds, so we got to multiply that by 60 as well. So that's going to give us our joules. So this would be 1,000 watts times 4 times 60. Okay, so that gives us 240,000. Okay, so that's the amount of electrical energy that the kettle has pulled from the wall in the 4 minutes that it has been operating. Then it tells us some information about heating the water from 22 to 100 degrees Celsius with 600 milliliters. We don't actually need to use that information because they told us that the energy output of the kettle is 54.4 watt hours of energy. So this is kind of a weird unit, watt hours. So let's break this down a bit. Watt is the same thing as joules per second. So let's go joules per second times hour. So there's kind of a mix and match of these units here. We're dividing by seconds, but then we're multiplying by hours. So to sort this out, we just need to rearrange these units a bit better. So let's go 54.4 joules per second. And then we've got hours here. So maybe I'll write it like this. We've got hours. We want to just get rid of those hours and convert that hours to seconds. So if we put hours down here and seconds up here, then we can say that 1 hour, 3,600 seconds. then these hours will cancel, and these seconds will cancel, and we'll just be left with joules. So this is a really weird unit that they use, but they use this for electrical metering all the time. It's usually kilowatt hours as the unit. But if we just follow the units, we can figure out how to convert that back. So 54.4 times 3600 is this big number, 195,840 joules. Okay, so all that, so that now we can do our efficiency calculation. So the output that we get, that number that we just calculated, divided by the input, times 1,000, or times 100%, sorry. Alright, so we get about 81.6%. For this one, we got a dryer with a power rating, and they're given a time again, 45 minutes. If 2450 watt hours was used by the dryer to dry the clothes during this time, how efficient is the dryer? Okay, so similar setup as before. We've got our power in, which was that 4356 watts. So let's actually go and calculate the energy that went into this thing as the power times the time. So we got that many watts, we got 45 minutes, and then we need to multiply that by 60 again to convert that over to seconds. So that's going to give us a number for the energy in. Okay, really big number. Put this in scientific notation. 11.76, or engineering notation, I guess, times 10 to the 6 joules. And then our energy out, in this case, we can reuse that same equation that we had from the last question, where we said that if we wanted to convert this into joules, we just needed to multiply this by 3600. Okay, big number. Last step is to divide those two and multiply by 100. So there's a times 10 to the 6 on the top, and there's a times 10 to the 6 on the bottom. So if you want to, you can plug it into your calculator exactly the way it is. But if you want this to be a little faster, times 10 to the 6 divided by times 10 to the 6, those two will be gone. So it's just a little shortcut to make this easier. So I'm going to go 8.82 divided by 11.76 times 100. And that gives me 75%. Okay, another big one. To compare the efficiency of a microwave with the efficiency of electric kettle, Kelly placed 50 milliliters of water into each. Kelly calculated the energy required to boil the water, which was 4.7 watt hours. The kettle, which had a power rating of 1300, took 142 seconds to boil the water. The microwave had a power rating of 900 watts and took 275 seconds to boil the water. Which is more efficient? Note 3,600 seconds in 1 hour. Okay, let's start with our efficiency equation. Okay, so we got energy out over energy in. Then the energy out is going to be that 4.7 watt hours. But if we do the same thing we did before, we just got to multiply it by 3,600 to get that into watts. Then the energy in for the kettle is going to be 1,300 watts. And then multiplied by time is 142 seconds. So that's going to be our setup for the kettle. And then we can do a similar setup for the microwave, and then we'll see which one is more efficient. So for the energy out, it's going to be exactly the same. The energy in, this one has 900 watts, and it took 275 seconds. Okay, so we'll do the top one here first. 4.7 watt hours converted to joules divided by the total amount of joules that the kettle took. That gives us, let me multiply this by 100 as well, put this into a percent. This gives us 9.17%. Okay, then same for the other one. That gives us 6.84. Okay, so from this, the kettle was more efficient. A 1 times 10 to the 4 watt electric motor is used to lift a 955 kilogram object vertically at 25 meters at constant velocity in 45 seconds. What is the efficiency of the motor? Okay, so let's start with our efficiency equation again. Let's say that that's going to be energy out over energy in. We can do this as power out over power in, or energy out over energy in, and both will give us the efficiency. So you can set it up just depending on what is more convenient for your question. So for this one, for the energy out, we are lifting a 955 kilogram object 25 meters. So you could think of that as the energy out would be the change in potential energy of the object. So that's going to be mg delta h. Then for the energy in, they told us the power in, so we just need to multiply that power in times t, and that will give us the total amount of joules that we put into the system. Okay, so the mass was 955. We get 9.8. We're going up at 25 meters. Power in is 1 times 10 to the 4. And our time was 45 seconds. So we're going to take all of that and multiply it by 100%. Then we'll plug this in and see what we get. Alright, that gives us about 52%. Okay, what is going on here? We have a force of 575 newtons pulling 11.2 meters of rope is used in a pulley system to lift a 1200 Newton object 5 meters. What is the efficiency of the pulley? Okay, so there's a bunch of stuff going on here with the picture, but I don't think we really need to worry about that at all. All that we really need to think about is that our efficiency is the energy that we're getting out divided by the energy that we're putting in. And so in this case, the energy out and energy in, you could think of this as like the work out and the work in. So the work that we put out and the work that we put in. So let's actually write it like that, work out over work in. Then we know that the equation for work is just force times distance. So there's going to be a force that we put on the output side times the distance from the output side, and then all of that divided by the force that we put in and the distance that that force was traveling on the input side. Okay, so now we can say that we can just plug in our numbers here. So the output is the object that we're actually moving is at 1200, Newton object, and that object moved 5 meters off the ground. We're pulling a rope with 575, so that's the force that we're putting in, and that rope moved a distance of 11.2. So then we're going to take all of this, do what we did before, and multiply this by 100% to get that out of a decimal and into a percentage. Okay, and that gives us about 93%. A 975 Newton object is pulled at a constant velocity up an incline with a force of 327 newtons parallel to the incline, as shown in the diagram. Assume that the difference between the work output and the work input is the work required to overcome friction. What is the force of friction along the incline? The length of the incline is 7, and the height of the incline is 2.22. Okay, so a lot of different stuff going on in here, so let's see what we need to do to sort this out. So, we got constant velocity, we're going up a certain height, and we have a certain distance. So let's think about this in terms of forces related to work and change in energy. So let me start with the work net from the system is going to be equal to the change in energy of the system. The net work, there's going to be one term which comes from that applied force, and then there's going to be another term which comes from that friction force. So the applied force is going to add energy to the system, the friction force is going to take energy away from the system, and then the change in energy of the system is going to be mg delta h. So constant velocity, so there's no change in kinetic energy, just change in potential energy. Now we want to figure out what is the force of friction along the incline. So we can break this up and say, okay, the force from the applied force, or the work from the applied force, is going to be that force times the distance, which in this case the distance is going to be the 7 meters, because that's the direction that the force is acting, minus work of the friction force times that same distance times that mg delta h. And the delta h in this case is going to be the 2.22, just up and down vertically. How high are we changing height? Now we got a lot of stuff to sort out here, but we can rearrange this equation. So let's bring our terms over to the right side. So let's subtract mgh from both sides, or mg delta h. And let's add friction force and distance to both sides, so we'll get them on the right sides. And then we got to divide both sides by distance. So we'll end up with the applied force times distance minus mg delta h all over distance is equal to that friction force. Okay, now let's plug this all in. I'm going to do this up here so I get a bit more room. Applied force was 327, distance was 7, now the mass was not given, but it's 975, so I'm going to replace m and g with 975 because that's the force of gravity. And then the height that we went up, 2.22. Divided by the distance again, which was 7. Okay, so let's see what we get here. Definitely could have done this in multiple steps, might have made this a little more manageable, but just did this all in one go. Alright, so that gives us 17.8 newtons for that force, so that's the friction force that we get. Now we want to figure out what is the efficiency of the system. So let's erase all of this and then we'll set up an equation for efficiency. Okay, so efficiency is energy out over energy in. And same with last time, we could think about this as work out over work in, and that would also give us a good setup. So let's maybe do it like that. Let's go work out over work in. Actually, you know what? Let's do energy out over work in. Both are going to be the same, but it'll work better for this section. So the energy out is our change in potential energy. So that's going to be our mg delta h. Then the work that we put in is going to be whatever that applied force is times the distance that we traveled. So we can plug in all of our numbers for this and then multiply everything by 100. So again, we have mg, which is the same thing as fg, so we can just put that in as 975 rather than solving for that mass. And then we got the change in height, 2.22. So that's the change in potential energy. That's the useful energy that we got out of this thing. Now, the work that we put in would just be our applied force, 327, times the distance, and that would be 7. Alright, if we multiply that by 100, we'll get a percent, which will be about 95%.